Yeah, so the next presenter is Mark. Mark has started as science operations engineer for planetary missions. His first mission was the Venus Express. That was a bus. No. So no, he said that no one remembers Venus Express because never sent any cool pics back. So see, his second mission was Rosetta, and everyone remembers Rosetta for the contrary. So now he's moved to a spice and auxiliary data engineer for ESA, and ESA planetary mission, which literally makes him the spice guy. So
Spice boy.
yeah.
Okay, my talk is rather boring, and it's really depressing to present after such a nice IPython, well, Jupyter notebook-based presentation. Mine one is dull and boring. I need to use the official layout for PowerPoint. But contrary to what was said in the previous talk of Orekit, I am here to sell you Spice. Okay, so. But the nice thing is that it's for free and it's really helpful. I think that this talk is very well contexted within the talks that we have just seen right now. Also because I should apply some testing to my own pipelines, which I still haven't had time to do. So here we go with the boring stuff. So ancillary data, it's one of those words which is not pedantic, but really knows what it means. So at least when we talk about ancillary data, we are talking about spacecraft or body trajectory and orientation, right? Now, we also often refer to reference frame specifications, not to confuse with coordinate systems. That's an error there. Instrument mounting alignment, field of view specifications, and physical and cartographical constants for the target bodies that we're observing. In your case, it's mainly the Earth, I assume. And also data needed for time conversions. Now, the purpose of ancillary data is basically to help mission designers, scientists to converge on a mutually acceptable orbit design, to compute the geometry of observations, and the conditions needed by operations engineers to do tasks such as communications, antenna coverage and pointing, thermal and power analysis, payloads operation scheduling, and then also to compute the observation geometry and the conditions needed by the payload teams to do observation planning, archive preparation, data analysis, everything. Right? So we need ancillary data for everything in space missions. Now, when we build up, so to speak, an ancillary data framework, we end up having something like this. This is an infamous sketch in which you can see like the space, you can see some objects. We've got the sun, we've got the position with respect to the solar system barycenter of different bodies. We've got the orientation, size and shape of a planet. We've got the same thing for a spacecraft. We've got models for the field of view of a given sensor in the spacecraft. We've got reference frames for the antennas on the Earth. So we build up on those blocks, reference frames, positions, orientation, size, shapes, pointing information, time conversions, and we get like the overall picture, right? Now, typically we use ancillary data in the following way. So on the one side, we've got the minimal information that we're talking about, especially we also might have even spacecraft clock correlation with your favorite time system. Then we have some software, and what we obtain from it is observation geometry in the shape of parameters, altitude, longitude, latitude, phase angle, whatever, and also conditions for our observations. So is the spacecraft in occultation, well, by Mars in my field? Is the altitude at the global maximum? How far am I from this other element in the constellation? Am I seeing it? Is the phase angle in the range of whatever? So we have to go from these ancillary data to actually what we want to exploit, which is the observation geometry. Now, a minimal approach to having this system would be at least to have a table of reconstructed time tag spacecraft position vectors, and the same thing with orientation quaternions. And probably want to have that using some sort of time tags, right, like UTC. Now, the issue is that when we have that, then the project leaves it to the end users to use this data with some other data and with some software that probably the users will have to have built in order to exploit this type of data. Now, if that's the minimal, so to speak, what you provide to your stakeholders, okay. Well, there's some advantages, which is that you might probably don't have to do much. You will minimize the cost, probably. And you also minimize the components of your project. But of course, there's some clear disadvantages. And I will just skip to this other fancy, old-fashioned diagram. So when you have this sort of minimal approach, the problem is that you have different actors that are generating different types of ancillary data. So on the one side, you might have your flight dynamics team, which is receiving the raw information, generating some sort of ancillary data that it's putting somewhere. Then you'll have someone in the ground segment processing that ancillary data, maybe to be provided to a science team or some other clients. And you have like another place in which you archive this type of data, or that you use to provide this data. And well, then the users may even have to do it in a different way. So as you can see here, the problem is that we are like, the ancillary data itself, it's basically, we're not controlling it. And on top of that, you can replicate this multiple times, because you might have users that use data from different missions, and in a cross-mission context, the formats and the conventions will change as well. So, what is the solution? The solution is SPICE. Okay. So, in a nutshell, that's the motto. So, SPICE is an information system that uses this type of data to provide solar system that includes the Earth. Geometry information to scientists and engineers in order to plan and analyze scientific information from space instruments, blah blah blah. It's originally developed by NASA, but naive at JPL, and basically the three, because if you do a list, I think it has to have 3 elements. So the 3 main points that I would like to outline is that it provides a large suite of software. I'll just show you something afterwards to read this data and to compute the observation geometry. It's open source, okay? So the code it's open and you can obtain it. It doesn't have any kind of ITA restrictions that were discussed briefly yesterday. It's the thing that you will ever see that it has been tested the most. It's extensively used, and there's way too much resources to learn it. Okay, actually, there's too much resources. It's also recommended means of archiving ancillary data by NASA, Planetary Division PDS, and the IPDA as well, the Interplanetary Data Alliance. So then you go from a system like this to something like this, in which you've got the different sources of ancillary data that you need to convert to SPICE format. But in this case, you don't have these many actors. You might have a team, a single team, that generates the SPICE data that you need. This is the types of SPICE data that you need then to run the software. I don't want to go into detail into that because there's no time. Or you could have a more distributed approach in which the knowledge on how to generate this ancillary data already in SPICE format is held by the pieces of the people who actually are generating the original data. So how do we use SPICE? We take the different data types that we need, which will probably come in a single directory or as a single Git repository, in the case for these planetary missions, or somewhere. You'll have a list of files that you have to load, and basically what you're going to do is that you're going to use a few of the SPICE Toolkit library modules. Okay, so there's there's a library, and then there's hundreds of APIs, and you will use a reduced set of them. You will run your own, and with that you'll have your program, and clack, you'll have anything you want to do. Evaluate the planned orbit, generate an instrument pointing plan, period generation, perform analysis of communications, science data analysis. Maybe, okay, let me go back. So the components of SPICE are the following. You've got the library of subroutines. As I mentioned before, it's around 1,500. You're going to use just use a few. There's also a reduced set of executables that you can obtain for your favorite OS, which basically encapsulate different APIs for common uses. Also, especially in order to generate SPICE data and to manage SPICE data. And there's a lot of documentation. So you've got highly annotated source code, it's amazing. 23 technical reference manuals and user guides. And you also have a complete training suite, let's say, available. And soon we also have the complete 3-day class in YouTube, if you cannot sleep at night. Currently, we've got 4 languages, Fortran, which is the core, C, IDL, MATLAB, but also with official stamp of the developers, we've got Python, and also we have JNI. It's available for all platforms. And right now they're working on SPICE 2.0, which will be based on C++, by the way. So how do we use it? Well, as I mentioned before, we can do many things. This kind of scenario is what we would have. So we could compute any kind of parameters, such as position velocities, size, shape, well, what I mentioned before. So we can solve the direct problem in any kind of geometry. I give you time and you give me the quantity. But we can also solve the inverse problem, in which I give you a geometry condition and you give me the windows of opportunity in which those conditions are met. Like, tell me when I am in between this range of distance with respect to this body. We are the ESA SPICE service, so we provide SPICE kernels for the ESA planetary missions. We also develop somehow in the evolution of SPICE, and we also provide consultancy of using and exploiting SPICE data for these missions. So it's a lot of work. For the last 2 years, it's been me. Now we've got some help from Brion Geiger. We have him at half time, and Alfredo Trini is here as well. There's a couple of things, very cool things that we also provide that I don't have time to go through, because as I mentioned, I wanted to sell you SPICE, which is Web Geocalc and Cosmographia. We've got training classes as well. Next one in Europe will be around 2020. That's my conclusion. Okay, extended. There's a poster outside which might be of interest, which is applying SPICE to the flying laptop. Another one by Nicola Altavelli on a more scientific application. I have a demo in the demo session, so you can just come to me and I'll give you a small demo. And we have many communication channels. So we are now on Twitter since last Friday. A site which is not really up to date. You can contact me via email, a GitHub page, which I'm working on, and all the SPICE kernels for our missions available to you. And that's everything. Thank you.
Thank you. So do we have questions, feedback, comments on SPICE? Oh, Pablo here.
Yeah. Hi, Mark. Thank you for the presentation. I have one question. I work in Earth observation at ISOC, and I am not aware of any activity regarding SPICE. What do you think that the SPICE could provide as an additional value to Earth observation missions?
It's true that so far that we know there's no Earth observation mission that has adopted SPICE completely. We know that SMOS uses it in a very reduced fashion. We would like to try to introduce it to Earth observation missions, at least for ESA. The thing is that nothing prevents anybody working on an Earth observation mission to use SPICE. You already have high precision models for the rotation of the Earth, as good as any other, maybe even the best ones available. So the only thing you have to do is that you have to generate the kernels on your own, which is not rocket science. So it would be simply that these sort of missions would integrate it in their systems. The problem is that it's not well known in the Earth observation community, or at least that's my impression. And people are not really aware of the power that it has. So the nice thing is that although it doesn't provide you like out of the box, I don't know, ground arc visualization or an ancillary data quick look tool, it's really easy, or at least it's not extremely complex to obtain or to build maybe components of your ground segment. I don't know if you were aware that it existed, so to speak. So sometimes I feel like a priest, I'm just now spreading the word on the SmallSat community.
You want to definitely get users to try and give you feedback, right? Martin.
Okay, do you hear about the SPICE software for electronics?
Yeah, when I was a trainee, I'm an aerospace engineer, so we used to use MATLAB in my university. So when I saw this, I was like, electronics. No, I'm not really interested in that. I know, yeah, we get a lot of that.
Maybe you should add something to this name, because everybody will be thinking about SPICE is just electronic software.
It depends on the community. Nobody in the planetary science community knows about the other SPICE.
But Google gets it confusing. Yeah. That's the problem.
I cannot change it, sorry.
Yeah. All right. If you have feedback, comments, you can reach out to Mark. And I think the best way is to join you at the demo, right? Yeah. And show what it can do. So thank you, Mark.